So we'll review the Euler versus axis or Darboux angle representations of either two-state systems or else actually a rotation of a rigid body. This talked about last time, but the main thing that I want to get across today about the Euler angles is that they're probably better at describing a state, and they are the polar angles, a twist angle of either an S vector. S vector doesn't have a twist angle unless you make it into a rigid body, or like the sphere that we have. And Darboux angles are much better at describing an operator that moves the oscillator or the rotating body. So we do need to make a connection between the Euler angles and these in a way that we'll describe fairly shortly here. And the application of this we'll look at, and that's rather interesting because that's where you rotate one thing and the other one is going half or twice as fast. That's, I think, one of the more mysterious things about the space we live in. It's a neat piece of topology. We'll go over what we just touched on very briefly, the A-type, the B-type, and the C-type motion. We'll do a little bit more detailed look at that. And then when you turn on two of these parameters together, that makes it a little bit more complicated. We'll talk about that as well. We looked very briefly last time at the avoided crossing, so those are important. So I want to spend some more time on the algebra of that as well as the geometry. And the ellipsometry, the polarization, mechanics. Now this is really optics, it's really quantum optics if you're talking about a quantum mechanical resonator of some kind, a laser indeed. So if we get time, I would like, and it's down here at the bottom below the end of the screen, so to speak, to show you the density matrix formulas that includes the block equation. And that, I think, is something that should be known by everybody in physics that does any kind of work with spectroscopy or optical dynamics and optical the optical effects in solids and condensed matter. So let's go ahead here. The first thing is the Euler defined state, where the state is represented by a spin vector at some orientation. But more than that, the state is also embellished with a phase of the oscillator that this is supposed to represent, the two-dimensional oscillator is supposed to represent. The machine that's sitting here on the desk that we played with a little bit last time is diagrammed completely here. You can see that this is the laboratory connection right here. This is the first frame that holds the axis that we call the beta angle and the beta dial. The polar angle, if you were, that beta rhymes with theta, so when you're talking about the polar coordinates of this vector in the frame of the laboratory, that's the lab frame view, polar angles of the zenith vector in the body of the rotor here, the sphere. And an azimuthal angle, which is this one down here, serving as normally we would, in polar coordinates, use the Greek letter phi for that. And then we use theta for beta. But then there's a third angle that represents that phase. If we're talking about a quantum two-state system, it represents, for a classical system, the phase in some elliptical orbit. So the analogy is very tight between the classical and the quantum by making use of this thing just in your algebra, but also here's a device living in the classical space that's duplicating the motion of a quantum two-state. And let's see if there's anything else I should say. Oh, yes, by all means, we showed a little bit about how if you were riding in the body, you'd be looking at this little red line here, the laboratory zenith. Laboratory zenith would be the thing that would be rotating around. You're attached to this globe right here, and the zenith of our globe, or the laboratory, is this vector right here. So it wouldn't be fixed in your frame because you're on board this carnival machine here, this for merry-go-round. The only thing that breaks the symmetry, so to speak, is, well, the azimuth angle here is this dial for the laboratory. For the body frame, it's got to be this dial, so that's the gamma. Well, and it's also because if I have this thing going, say, counterclockwise, then the people on board that thing would be seeing the laboratory, that's this thing, going clockwise, the opposite sense. So a negative sign goes on all of the angles that are being used here. There's the beta, even the beta. The beta they share, but with a minus sign for the body. The gamma and alpha they don't share. The gamma and alpha are separate dials. So this is sort of the connector right here between this space and that space, and the dialing reading is telling you where you are with regard to polar angles for both of them. Okay, does that make pretty much sense? So this is a lot more information and a lot more visualization ability than this is what you see in every book I can find. This is an improvement. And it's Hirschbach, Dudley Hirschbach, is a sort of physicist chemist. He straddles both worlds, and he has offered to use Harvard money to make another one of these, and so we're going to, I said last year we're going to do it, and we haven't done it. It's just a matter of picking up the phone and doing something, so that we hope to happen. And then we'll use transparent or spheres so that you can see a spin vector inside there.
Also in parallel, it's still not quite finished.
Yes, this is this thing right here.
Yeah, we have a web-based attempt at this, and some of the dials aren't quite aligned properly.
I'll just turn it on, but I won't try to do much, but just to show you what it looks like. Let's see if it...
See, now that's going to launch it in Chrome, and Chrome is really bad in WebGL.
Yeah,
so it renders it, but when you try and rotate it, it stutters.
Yeah, it's slow. It acts slow, it acts jerky. But anyway, and the advantage of this one is we don't have to stop. This one, you see, you can't put this crank through that bar right there. When I first made this at Jill, and I wasn't the one that made it, there was an instrument maker that's so fascinated by a picture I had in a Reviews of Modern Physics. He says, let's make one. I mean, that's very rarely happens that somebody in a machine shop makes more work for himself. Usually they drag their feet and say, oh, okay, I'll get it by the 2 Thursdays after the next Saturday. But he just went around and he got all the pieces of things that he, anodized aluminum that he'd thrown away, and he made a great big one with the rings the way I had drawn it. But the problem with that was, you can imagine if there's a ring going all the way around here, I can't rotate very far, and it runs into it, you see. So when I got the Georgia Tech, I fixed that deal by making a quarter ring. But you can't go through that. So you're still limited, but it's a very small part of the parameter space. And you can do the stuff we're going to talk about today, where you get the 2-to-1 ratio between spinning and rotating.
So I wonder if you could make one that's electromagnetic. You could just
that would be cool. You mean just put them in some sort of support?
Right.
And those are the fancy supports that use nonlinear resonance to really levitate.
Right.
Yeah, that's a thought. And then you need another one. You have to levitate a levitator, right? But it's within a possibility. Yeah. Then the problem, of course, would be locking it down. It would be moving all over the place. This thing, at least, you can tighten the screws here to make it so it stays more or less in one orientation. The context menu for this thing lets you set dials, so that seems to work pretty well.
There's issues with that as well. There's some multi-value miss that you'll actually cover later on in the class. That's not
We're going to do that
handled.
almost immediately. The question is, how do you convert numbers over here into numbers over here? But even harder is, let's say I know 2 numbers over here and 1 over there, right? That's the sort of situation you might run into in some configurations of this business.
Yeah, we're just changing your views, transferring from Darboux to Euler. You have to take this.
Yeah, and that's really the next topic here. Let's go back to
And those will also be listed under this calculator when they're rolled out. It's a little bit of cart before the horse, though, I'm afraid.
Now, we looked at this before. The sequence, alpha, beta, gamma, that's the way you write it down, the 3 operators. But the thing on the right acts first, right? Because we always have cats sitting off here to the right. So when I have the product of alpha, beta, and gamma, gamma comes first, okay? And you saw why that had to be. The ball's already lined up at 0, 0, 0 on the settings of the dials, okay? So this thing is lined up with the laboratory Z-axis. So you bring up the laboratory Z crank while this thing is where it can be cranked. Later it's going to be over here someplace. I can't crank it with a Z anymore. I just get one chance at that. And then even no matter what you turn that thing, you're still lined up to use the Y crank. And so you turn that to just tip the thing to some polar angle. Then the last thing you do is get that Z crank working again, this time to set the alpha, the azimuth. Okay, so that's the sequence that we talked about that leads to the 3 coordinates for a rigid body. That's the topic of Unit 6. But here it's 3 coordinates, 2 of which define orientation of the vector, and the third is the one we set first, and that's the phase. The phase is actually gamma over 2. The mysterious 2 shows up right here in the matrix that acts first. Then there's the beta, and then there's finally the alpha that puts a different phase on the top and the bottom, a minus alpha over 2 on the top, a plus alpha over 2 at the bottom. And then it puts cosine and sine of the beta. The beta determines your going from the ground state to inverted. That's population inversion when you crank beta from 0 all the way up to pi. In a 2-state system, that's the best you can do. Okay, so the question is, how do you deal with converting these coordinates to an operation which in one step would convert this to that? You see, that's what Darboux or axis angle rotations can do. There is a single cranking that will get you to the place that these 3 get you to. But those 3 make better coordinates. The other one makes better operator visualization. So that's what we have to do, is we're going to use operators to define states. Then you definitely need the Darboux to Euler transformation.
And so this Darboux rotation will also have the same phase as the Euler?
It better.
Right.
It better. Yes, absolutely. As the thing is turning it through those things, all the dials are moving, including the gamma.
Okay.
You see, and that's what you see when you play with this thing right away. It's pretty hard to turn this thing without changing this gamma dial. You have to be perpendicular to it. Okay, before we go on and do that, let me remind you that if you're doing this algebraically and you're interested in the components of the spin vector, those components are defined by alpha and beta in the normal polar coordinate way. Beta is theta, alpha is phi. Okay? And gamma's out of here because we got the expectation value by something that can only give real numbers. This is complex conjugation doesn't affect any of these. You see that you've always got the star thing next to the unstarred thing. So the complex amplitudes here, or even when you have an eye on the thing, there's no complex numbers left. The answers all come out to things that are real. Assuming you haven't decided that you want to make x1, p1, x2, and p2 complex, that's getting crazy. But sometime in my, I've thought about things like that. You can always complexify something that's already complex and get in a lot of trouble. Anyway, the only one of these that you would recognize immediately as a single quantity that's sort of outside of what the energy is here is this one, x py minus y px, if 1 and 2 are x and y respectively. So this one right here, the c, is actually the angular momentum of the two-dimensional oscillator. And it is two-dimensional, so the angular momentum always perpendicular to the plane in which the oscillator is constrained. So that's interesting to know. The thing I didn't mention was the color notation here. If you're red-green colorblind, neither of you are. So you can see that this is sort of an orange and that's a red, as best that we can do right here, and the axis is the same way. The green is for go. That's the way you get current going, is to have something that isn't just 0 or pi out of phase with the other dimension, you say. So that when this thing opens up, there's actually circulation. This is just the other reason for using the letter C for this C for crazy too, because it's got the crazy complex stuff. In any case, that's something I want to look at a little bit again today. But first, overview. What we have is a two-dimensional oscillator. So we started the discussion of this off quantitatively by using all the information, namely the 4 dimensions, real and imaginary of the two phasors. And that's as much as this system has. Those are all 4 degrees of freedom. But if you plot just the real part of one of them versus the real part of the other, then you'll get always some kind of ellipse. Or if you have various things actually moving, you can get all kinds of Lissajous patterns. But the idea is that this is a pretty good way to visualize what the oscillator is doing. Just do its coordinates against each other. Then the other 2 dimensions, which are the 2 momenta, are there too. And we'll look at pictures where you draw that as well in a diagram that you have to look at stereographically, because it's a 3-dimensional projection of a 4-dimensional space. Okay, computers do that very well. If you get good at visualizing that for certain things, it can be helpful. But this doesn't have that, you see. This one just, for the simple polarizations, has just an ellipse. It's some shape and some orientation. And so you're losing here the overall phase until you actually look and see where it is on the ellipse. But aside from that, you've gotten rid of some information. This is the other way to get rid of information. Here the overall phase is hidden in the gamma dial, But for most people that do this kind of stuff, they would say it's just not there. It's been killed. All we have is 3 numbers here. So that's okay, because the complex things that this thing can do are mostly described by just a spin being somewhere and then going somewhere else. So this is 3 ways to visualize that we know of. The fourth being this machine, which sort of does all of that in a way that you can see. Okay, I think that is all I need to say as we go on here. Of course, there'll be some examples later on, but these are 2 that are pretty typical. If I'm really in the let's see if that's right, the AC plane here, I will have an ellipse because I've got a component. Whenever I get out of the AB plane, I open up an ellipse. The AB equator, you see, is only for plane polarization. As you go around that plane, you don't make an ellipse at any point. But as soon as I have an angle above that, that's the copolar angle there. Polar angle, if you're using the C as your Z-axis, would be here. But if you're using A as a Z, and that's what we're doing, right? When we say Z, this thing right here, this axis right here, what we're meaning is Pauli Z, and that's A for us, right? The asymmetric diagonal, the 2x2 Hamiltonian, right? Looks like a Z spinner, a Pauli Z spinner, okay? Then this is the polar angle, you see, with respect to that axis. So where do you want to put your axis of quantization? We need a clever way to do that, and we'll talk about that later on. Depending on what kind of experiment you're doing, you like to line up as much as possible with the eigenstates of the Hamiltonian that's at work, or the major part of the Hamiltonian that's at work. So you'll have a 2 psi, and that will show up just in this thing right here, psi or nu, depending on whose notation you use. The different, lots of different conventions. Half of this angle is the aspect angle of the ellipse that you're making. You see, and when that closes down, that puts you back on the equator, and the ellipse has no C component, and it's just plain polarization. It's like a standing wave as opposed to a moving wave. We'll get into that idea later on. Then if you have an ellipse and you start to rotate, that's called the Faraday effect. It's amazing that Faraday could deal with something like that without any of this ways of looking at things. But as soon as you do that, you make an angle with respect to the, in other words, there's the ellipse axis right there, sort of tangent to a square that it might be confined to by some Hamiltonian. But that angle is shown by the azimuth angle in the AB direction here. So 2 phi, this was phi. Okay, so that's 60 degrees if this is 30. Remember, everything over here is going twice as much or twice as fast as everything over here. So you get those factors of 2. And if there's anything else I can think of right now, this is a weird angle right here. We'll try to talk about what's the physical significance of that. That's basically when you draw a bunch of ellipses, where do they cut a plane that you look at? You basically look at where it cuts there, and you can read the angle. It's something that you have to see in order to explain. So those are things we wanted to talk about a little bit today. But still, the basic idea is that the complex U2 ellipse, it's got lots of complex numbers, 2 for there, 2 for there, of any state corresponds to a single point in this spin space. So that's a tremendous efficiency in visualization right there. Just a point on a sphere means, and this thing can be doing whatever crazy things it's capable of. It's just another point. Now that number point, depending on how much noise you have in the system, basically, or how depolarized is your system, this is where statistical mechanics comes in, is the size of the sphere. Now it can be out at the maximum, and then in that case you're fully coherent. There's no loss due to decoherence. But as you take light and just put all kinds of different lasers together, different frequencies, finally you end up with something that's completely depolarized, and this thing just collapses. You know, what polarization? Well, it's all of them, or none of them. So that's something to remember. That's where the density matrix formalism comes in at the end. To do that efficiently, just uses this stuff in a slightly different way. Okay, so there's another picture of the two worlds. The U2 world with ellipses that have angles and phases, and a R3 world where you have real 3D vectors, but we don't lose that other dimension if we use the machine that is stuck to some spin vector. And then this is the crank vector right here that's going to whirl that spin vector around and twist it a little bit so it changes the gamma number that's sitting outside of the spinner up here. All right, so the real point, I guess, is that R3 world is labeled by 3D spin vectors, this guy, okay? And their angular momentum, if you were thinking about the spin vector of the electron, which was the second thing to be looked at by physicists, and this is in the 1920s to 30s, long time after Stokes, who really deserves to have the S, because he's 1863 with a theory of polarization, they say. And that is a pseudo-angular momentum, but it's also an angular momentum. But any two-state system has this S to it, and for many of them, you can't really say that it's an angular momentum. It's could be, you know, in the equatorial plane, there's no angular momentum, but the spin vector is a quasi-spin, and that's the name that's being given to it. Anyway, whatever that is, they're driven by, and this is the operator that's rotating, a 3D spin vector. This thing, crank vector, is what I call it. Okay, so that's the crank that's sitting outside of the ball that has the spin attached to it. Okay, make enough sense there, and the various notations using polar angles that we'll talk about very shortly here, and then the alpha and beta polar angles that a spin vector has. Okay, well, the crank vector, I like to apply the name of the geometer Darboux. So the Darboux angles, as opposed to the Euler angles, are the angles that describe the operator. So here's the stuff that's described by Euler angles, alpha, beta, and gamma. That's the spin vector with the body attached, so we need three angles to orient that. And then this thing's going to come along with its three polar angles. And the machine makes those fairly obvious. There's a dial here that reads the polar angle, and then there's another dial around the base here that's in the same plane as the azimuthal angle of the body, the Euler angle alpha. But this one is to handle the crank. You see, put the crank in some position, you say. So the first thing you do, I suppose, you set this thing to some orientation, and then you move this thing on there by unscrewing it a little bit. That's the brake for that. This one doesn't need a brake, so much friction, and just aluminum on aluminum. So that's the set of polar angles, and this one is usually dynamic. So we assign an angular velocity to it. That's the big omega, and this is the big theta. And we've already used that notation a little bit when we were putting the algebra together. So I use an italic phi and italic theta for the ordinary polar angles of azimuth and polar. So that's the three angles that need to be connected to the alpha, beta, and gamma. Okay, the spin vectors there are being given by polar coordinate to Cartesian conversion. These are the same, but therefore a crank vector. Okay, so the idea is you can define a state by the operator that brought you there, or you can state it directly by the Euler angles. This is very convenient, as we've seen already. They're the dials that indicate that. Here are the three of them, actually in the photograph. Okay? So you notice we used to have a little tag that said this was a rotational analog computer. It's not exactly what it is, so whether you have the tag on there or not. In any case, here's what we have to do. Realizing that the Euler angles that or operations that were very special, that we talked about in lecture 22, those three, gamma followed by beta followed by alpha, will give us a state, and that state is going to be represented here, at least the operator that got us that state, is going to be represented by coefficients of a unit matrix. Then the what I've got here is the B bilaterally symmetric Pauli spinner. Okay, well, it's first here because we're really thinking of that as the X Pauli spinner. Then the next one is the crazy guy C, but that's Y. And then the last one, this was the first one for us. This is the AD, it's the asymmetric diagonal spinner, but that's called Z, the third in Pauli's lineup of operators. Okay. So that's defining any possible two-dimensional operator. Has 4 parameters. You only need 4 base matrices to define it. Use the same base matrices over here to define this guy. And once you've done that, then you have coefficients of them. And here's one of the coefficients right here. Okay, sine theta over 2 and cosine phi sine phi. And then sine phi sine theta. And finally cosine theta, those polar coordinates right there of a unit vector. Okay, and all of the vector components get a sine of theta over 2 attached to them. Only this one, okay, gets a cosine of theta over 2, and there isn't the azimuths for it. It's just a unit operator. So this is the one. This is going to have a connection to time in a relativistic transformation. So right now, all of our activity is happening with these 3. So it's this matrix right here that defines the operation that takes you to a particular place. Well, where? The only way I can name my where is to use this stuff, you see. So that's where the conversion comes in, you see. And how do we do that? Well, as I say, we just broke it down to there. So as I say, these make better coordinates. And we've got to relate these because that makes better operators. So there's our Euler matrix giving us a general two-dimensional oscillator state with x1 and p1, x2 and p2. Then writing it out as a spinner, okay, this is the phase coherence angle, alpha, the shadow, you might say, of the spin vector on the thing that's down here. You see the shadow of that spin vector is being given a polar angle, okay? And if you're talking about a classical transition in atomic physics, you're talking about a transition. It isn't really a transition. You just think if you're pumping a two-dimensional oscillator with a field, you're actually thinking of a one-dimensional oscillator has a phasor. So then the alpha is the phase angle of the phasor for a spin vector that never gets very far, you see. And that's the thing about the classical transitions, was that until the laser came along, about the best you could do was, you know, sort of get out to the border of the town and go around in a circle at the frequency of the transition, you see. But, you know, getting it anywhere far from town was really out of the question. And being actually to conceive of the fact that phasor space was round, in the sense that you could go out far enough where you started to, your shadow started to come back, but you're up here with all this energy. That's the population inversion state, which is so mysterious at first. When transitions started to become coherent for an atom, they could actually go all the way and then come back again, you see. So it's like Columbus now saying, hey, phasor space isn't flat, it's round, you see. So then the alpha, you see, was the only angle that you play with. This thing was just an amplitude that you made big and small. And most of the thing, it was all here, and you didn't even think about what was here. So that's the classical transitions. That's what Lorentz was working with when we did our Lorentz theory. That's the way he thought. Okay? So now we're finally paying for all that. We're going to make it so that we can take these numbers here, including the phase, and assign them to the four numbers that are involved with this device here. So to do that, we've just barely, we're going to connect the coefficient of this guy right here, that's cosine of the actual angle that this operator rotates, over to, okay? We're going to equate that to this guy right here. Okay, so that's our first equation. It's the equation for the real part of the first component, which at the DC level for the Lorentz oscillator is about all you've got. Okay, you don't have any momentum to speak of. You're just, you know, going really slowly, right? And finally, not at all. You just put a static electric field on it, you get a certain X1, right? That's the susceptibility, the linear susceptibility, okay? So that's X1, we got an equation. And basically that's what it's going to boil down to. We're going to have an equation for each one of these four things. And that's the way we do this four-dimensional polar coordinate to rectilinear conversion. Four-dimensional polars, four-dimensional rectilinear. Now there's two kinds of polar coordinates, the Euler kind and the Darboux kind. This one looks more like what you're used to, except it's got more factors. This one's weird because it's got two angles, plus and minus, half sum and half difference. Okay, this is P2 that I take next right here with a minus sign. Oh dear, that thing is. We've got to figure out. Oh gosh, you put your pack on top of it. That's what it is. Yeah. It's not a big deal. Anyway, so as we go through, the next one is the X2, the real part of the second component, and then the one after that's the imaginary part of the second component. So all we're doing is connecting each of the components here to the corresponding components there, and then realizing that that's what we're doing here. We're just connecting it to the Cartesian way of looking at that four-dimensional object. And they're actually getting the components of the four-dimensional object in the process, expressed using one set, that's the Euler, and the Darboux set there. Now, what's Darboux known for that gets this name? And what he realized when he's doing mappings is that whenever you do a mapping, say a mapping of a sphere that's here, and then I with whatever angles I turn the sphere somewhere else, there always are 2 points in the neighborhood where that haven't moved from where they were before you started the motion. I mean, that's kind of weird to think about, but in fact, the whole idea of mapping, if I hold a map of Fayetteville up here, and this is Fayetteville, so there are points here that are on that map, right? Then there's a point on that map which is actually a point in this room. And I move a little bit, and then that point moves just a little bit on the map, okay? But in the room it moves whatever I say, okay? I move an inch here, and then the scale of the map is 1 to 1,000,000 or something. I move 1,000,000th of an inch, right, on the map. So those correspond to 2 points that are in the same place before and after the motion. But with a sphere, there are 2 points, one on either side. And they're this guy. You see, those are the points that don't move. You see one here and one there. Didn't move from when we did this rotation at first. And as you turn the crank, they continue to be the same points. Okay? When you do Euler angles, that point could be jerking all over the place. With a pair of points, that line goes through the sphere that represents the fixed points. So, you know, this makes your head hurt because very few people Darboux thought about it a lot, and therefore I think he deserves the name, because that's really what we're doing when we want to find eigenvector rotation. That's what we look for. Okay, so it's just a matter of doing an algebra of this. I'm going to go through that pretty quickly. This is what we just wrote down by making the connection here. So now we want to actually solve an equation that gives these guys in terms of those guys, okay? And this is a pretty good start right here, okay? Just noticing that if I take these two, divide this one by this one, so I get sine over cosine, I cancel this guy, right? So I get sine over cosine as tangent of the half sum, okay? And I go over here and do the same thing, okay? Divide this into that, you see, okay? So I get sine over cosine. That's a tangent of the big theta, and I get a tangent. I'm sorry. Let's see if I've got that right. I divide. I get a cosine. Cosine is that something weird. Oh no, I'm looking at the wrong guy. This guy right here. Okay. I get a tangent of this guy right here. Okay. And it's this thing in the numerator, right, is equal to the tangent of this guy. So there I've got one kind of angle on one side and one kind on the other. That's a good start, all right. It turns out I can also do it with the second thing here. Here's tangent, again, when it's one, I'm using these two guys right here, this over that, okay. So I divide this over that. You can see it canceling the sine out, but it's leaving, and it's also canceling that out, but it's leaving it with a tangent, actually a cotangent, cosine over sine of the phi, right? This cancels, that cancels, right? So what I can do with the cotangent is make it a tangent of pi over 2 minus phi. I get a tangent of gamma minus 1, half difference of gamma and alpha, okay? So you just set this angle equal to that angle with a little note to yourself that you might have to put an extra 2 pi on either one of them and some multiple thereof. And that's true of all of these equations when you get done here. So that's a really nice, if all the solutions were like this, it would be a linear thing we're solving, right? There's a nice linear equation that comes out here. So the half difference of this, it's got to be the Darboux phi. It's kind of neat. No matter where I put that crank, it's the phi angle, which is this angle right here. Something that's telling me the half difference. Okay. And then, if I'm interested in a sine of that half difference, I can go ahead and write the sine of this. So I get another equation right away. The sine of the half difference is a cosine of the phi. That's another way to write that. But we need this one to substitute into some things that we're going to do next year. This one just boiled down to gamma alpha plus, right, half sum instead of half difference. That's the arc tangent of the cosine and tangent. That's a solution, and most of the solutions look like this, some sort of arcing. And what that means is, and I put a note to this at the very bottom of this, is that if you're taking the arc tangent, you'd better find an x and a y and use the arc tangent 2. Are you familiar with the arc tangent 2 when you're programming? Instead of using just plain old a tan, you use a tan 2, and it takes two variables, x, y first, I think, and x second, right? So it knows what quadrant it is. Just this, just an arc tangent doesn't know what quadrant it is, so you can be off by a huge amount, to pi's, pi over 2 off. Okay, so that caution certainly is to be made here. Now, putting those all together lets me separate alpha and gamma. So this is the actual equation for alpha and gamma in terms of all three of the Darboux angles. And again, a tan 2 should be set up there. I'm not showing how to do that right here, but if you look at the spin vector where it is, you can make it a quadrant. And then finally, this one right here lets me use an arc sine. So there's alpha, beta, and gamma in terms of those guys. Okay, so these are the coordinates of the thing after I've done this rotation. It can be anywhere and by any amount. I'm going to be able to get these things. Okay. Going the other way is a little bit more difficult. We already have a part of it from this one. So I've got the linear relation right there. Okay, but the other two, it takes a little bit of argumentation to get those. But I've outlined with these lines what was used to get that. This particular one is an a tan of a tangent. Now, that would immediately give me a beta if this darn thing would just go to 1, and all it requires is that alpha plus gamma would be pi, so sine of pi over 2 is 1. Then in that case, the arc tangent cancels the tangent, and I just get this thing equal beta over 2. That's an interesting solution, but not very useful. However, just one more step here with this, and I'm using the x1 equation. I've got an arc cosine of a cosine and a cosine. So this is another one which would be canceled if one of those two factors got to be 1, but most of the time they're not. So there we have just the opposite of this. So we try it out. This is the one that's in the textbook and in most of the lecture notes, alpha 50, beta 60, gamma 70. Okay? It's telling me that in order to get to that setting, I've got to, first of all, set the crank vector, a polar angle, to 33.7, and it's really hard to read a 0.7 on that dial, so you just get 33 and then a tiny bit. And then move the whole crank around until it reads 80 degrees at this point right there on the dial of the phi, okay? And then turn by 128.7 degrees, okay? So these angles, these numbers here don't look anything like these. But we try it with a machine and it works. We'll show pictures of that shortly here. But as far as doing a calculation with a computer or a calculator, it's worthwhile doing a reverse check using alpha, beta, gamma in terms of those angles. Okay, so I get an alpha, beta, gamma of 50.007. Well, that's because I didn't give the thing in 5-figure accuracy. And then finally the beta is coming out not to 60 but 60.022, and the bottom one there is pretty good. It's 70.007, 007. James Bond was responsible for that one right there. So it's working, okay, as best you could expect a digital version of using this transformation. Okay. Now, the next thing, as I said, was something I usually do right here in the class, but it's hard to arrange exactly this one, but I can do it approximately. And the way you do that, if you point your camera over this way, is you release this thing so the crank is out of the way, and you reset the Euler angle machine so that it's lined up with the this thing on the y-axis, and then you turn them all so that the gamma dial goes to 0. Okay, gamma dial is turning your twist here, you see. So I'm going to stop this thing. So I have my minus x on top of each other, my plus x on top of each other. The x bar is the coordinates that are on the body, the x's and y's, these are the normal laboratory coordinates. And then, say I'm going to do a rotation that's over there, I attach the crank and suction cups, hopefully hold. It actually helps a little bit to put some spit on them, because there are going to be some points where the thing has to actually apply some torque to make it go. In any case, I attach this to the body where there's the fewest number of marks and things to let the thing out, and tighten this little set screw right here so that it keeps the thing down. Okay? Now if I turn now, nothing's going to happen. What I have to do is help it a little bit and get this thing here pointed in that direction. And then I can break free to start my rotation, you see. Now, right now the top of this crank was right at the top. Okay, so here is a about 180 degree rotation now. Okay, and you can see all the dials are changing. Okay, and finally, as I bring the crank around to the top, I return the ball to its original position, the one I started with, as far as the ball is concerned. But there's something that isn't home right now, and that's the whole framework, right? At this point I can cut the framework loose and just spin it back to here, and then it would be the same settings. But those Euler angles are different than they were to start with, okay? What I have to do is continue rotating, you see, another 2 pi. Bring this thing back around to the top again, right? The crank thing lever over to the top. And that right there is where I started, okay? Well, that's what this sequence is doing for this 50, 60, 70 settings. So right here, 0 degrees, okay, I'm talking about the Euler angles that, let's see if I've got that right. This is the Darboux angles right here written out, and the Euler angles, let's see if they're written out here, here, and here, and it's hard to see them, but that's the 60, 70, 50, 60, and 70 degrees on those. And then it starts turning, you see, like 60 degrees, 128, 180, 240, and so on. Now this one right here, at this point, 128.7, remember that's the magic one that gave us 50, 60, 70. So there's that point right there. It had to go through all that to get to here. And then they keep changing as we go around there. So there's 300 and just a little bit more and I would, this would swing in, and I'd be back at the starting point that we had here. Was 0, 0, 0. It's not going to be 0, 0 here, because this thing, you see, is on this side now, just like that one was on the other side. This one started over here, and it's now gone that far. Okay, so what do you do next? Well, you just keep rotating another 2 pi, another 360 degrees, okay, from here. You see, there's 360 right there. That's the, would have been the next one. It's now down here, okay? And what it's got is 170, 0, 190 instead of minus 10, 0, 10, which this had, okay? And you had to have that 10 and minus 10 because otherwise you couldn't move the crank. It's gibble locked. Okay? So now it rotates one more 2 pi to 660, and 720 is that. Okay, so there's your 2 to 1 business happening in this room with classical stuff. Okay? Now, can you think of other ways to think about this? This one definitely nails it, but it's still hard to visualize, you know, rotations. You're just not equipped. These, and I've studied them for my whole life. I've never gotten any better at really seeing. As soon as it goes around the corner, I've lost it. You know, in terms of total view. So, what else can you do? Well, it used to be physicists were famous for basically partially disrobing in order to explain this stuff. And you can imagine Trump explaining this if he was a physicist. Of course, he is nowhere near that. But in any case, what they do is they take off their belt and basically do this. Well, if their pants didn't fall down, this isn't very enlightening. Something else needs to be said. And then there was a patent that would allow you to put a wire into a turntable. So the turntable is just going to rotate using the motor here to go through these gears and turns the turntable at some speed determined by the gear ratios. But the idea is that these wires, which are attached to this, and they can be attached to some motor or light or whatever in there, the idea is that I don't want to get them twisted. So what I do is, and that's what the purpose of these gears is I make something that rotates this thing half as fast as the actual turntable rotates. And so it never gets twisted. And that turned into an invention of a periscope that would let you, if you rotated the prisms here half as fast as the turntable rotated, that you would always see the image of the arrow and the turntable stationary when you looked into this periscope. In other words, you'd look in this periscope, your eye would be right here, and you'd see the arrow, say, up, and it would stay up. You would be riding on this turntable. You ever seen this thing? I think we should build one. It's kind of cool, and then do it so that you could really rotate it fast, and you could see some of the funny things that were happening on the table there, as though you were riding on the table, right? So that was one invention that really starts to make you see what's going on here. And of course, it's the carriage here going half as fast as the actual ball is, right? Okay. Now, I'll give you a demonstration that you can do at home of how it works. It's very simple. I don't have to take my belt off. Take the thing. I've got the top of this guy pointing at you. So you imagine doing this with a cup of water. You see, half full. Better be half full, or you're going to spill. The idea is not to spill it, but rotate it completely around. You say, oh, I can't go any further than there. But yes, you can. You just go around like this, and now it's back again at you. Okay, and then I come up here, and I keep going. And now it's back at you again, right? It rotated 2 times. And I didn't break my arm or disjoint my elbow. Okay? So every cheerleader, right? Every, in high school, they hear the people with the batons, right? They do this all the time, even when they're burning. So that's that. If you're going to, see about this 2 to 1, there it is. You can feel it. Okay? That's the best I could do as far as saying much about that real magic. Now, here's a very practical thing for algebra. If you've got this matrix, that's the general 4x4 Hamiltonian, how do you find eigensolutions for it? Okay, and step 1 is to find the Crank factor as to turning there. You have this thing broken down into those components. You convert the Cartesian form. Okay. So whatever those numbers were, you figure out what the A, B, and C are, or vice versa. You just put these angles into this and get the A, B, and C. And then the first thing that you're getting is this number right here. That's A plus D over 2. That omega 0 comes up quickly. But then this one right here involves all 3 of these numbers, all 3 of the A, B's, and C's, and D, all 4 of them actually, but it's the difference here, it's the sum here. Okay, so that gives you your basically your beat frequency. Okay, now the beat frequency over 2 is what you're actually going to get. The eigenvalues are going to be this, plus and minus that over 2. These are the actual eigenvalues of that thing, just worked out by algebra, and it just involves this quantity right here and this quantity right here, okay, being summed and differenced. So what you're doing, you see, for a 2-state system, is you're trying to find, first of all, the omega 0, which is sort of the average of the 2-state eigenvalues, and then the beat frequency, which is the difference between these two. That's the only you actually see in the 2-state dynamics of whatever wave it is that this thing is representing. And that corresponds to a plus over 2 and minus over 2, getting together to make something you actually observe, which is the omega, the beat frequency that sits outside of all of those things. So there's your omegas. And then you get the other 2 angles that actually tell you where this thing points, where this crank points in the Darboux coordinate space. Okay, so I go ahead and solve for each of those angles by taking arc cosines. It's not the best way to do it. You can work this thing around to an arc tangent using tan too. But in any case, the eigenvectors, that's the azimuth alpha and the polar beta of the Euler eigenstate. Okay, so we're after here. We're interested in the that particular one from the 0, 0, 0 state, and an operation from the 0, 0 state to this particular one, with the Darboux angles as the azimuth and polar angle. Okay, so the angles that we get here will correspond to basically treating alpha as the phi and treating beta, the polar angle there, as the theta. So beta gets to be theta, alpha gets to be phi. And there's your eigenvector. That's the formula for it. And there's where it is. It's the crank vector sitting at the point of the S vector. You need 2 solutions. The other solution corresponds to just putting a pi onto this theta, leaving everything else the same. This is the crank pointing at the butt of the spin vector. So it's spin up and spin down in this particular, for this particular Hamiltonian that has these Darboux angles, whatever they are. Okay, so I think I'm going to leave that one there and speed through this lectures until we get to this point. And you can review very quickly what we've done. Mostly it's algebra, and then rotations, and there we are. What I want to show you is, we'll start right here. Can you write down all the eigensolutions of the following Hamiltonian matrix in 60 seconds? Remember the movie called Gone in 60 Seconds? This is about car thieves, right? Which we have 2 of in the Congress now. Anyway, take this matrix right here with A and B and C equal to what you see there, D equal to A equal to 12, and then find the eigensolutions, not just the eigenvalues, which you get fairly quickly by doing the thing right here, okay? So this is my base average frequency. Omega 0 right here is 10 for this one, A plus B over 2, A plus D over 2. And then omega is the Pythagorean root of the 3 numbers, okay? So the omega, the thing that's going to go right here with a 2 under it, but actually it's the beat frequency, is 8, okay, in this case, all right? Now, where is that vector? You see, that's what all the rest of this is, okay? They're the eigenvalues that you would have by adding and subtracting, okay, this. 10 plus 4, 8 over 2, and 10 minus 8 over 2, okay, is 14 and 6. So you've got a 14 and 6 as your actual energy levels above some arbitrary 0. And then the last thing to do here is go ahead and work out these angles. Okay, arc cosine of this thing into A minus D. And then arc cosine of B into just those things. So there you are. Then it's just a matter of making a picture of that. Once you have that, those are the eigenvectors, okay, complete with all their phases. So that's what this basically is, this formula right here. So once you get this one, it's easy to put a pi on it, and you've got the other one. Okay? Well, it took me more than 60 seconds to actually describe it, but with practice, right, this could be done, you know, quite easily. And of course, if you're going to program something, follow this pathway as well. Okay. As I always say, a more reliable computation with a computer is the A tan 2 between C and B. The arctangent of just the ratio of C and B is pi unreliable. Okay, now I'm going to race through this part right here and get to some examples. We've already looked, I think, at the examples that involve the A type motion. That one just made a rectangle of listed U patterns that filled it up. So I'll not do that one. But in any case, there's the diagram. The quantum mechanics people would like to show the level diagram. And then there's you know, just a sketch from the old color U2 application of the thing. There's the thing we looked at yesterday, right? A-type motion with the crank right along the A-axis. Actually, this one was opposite the A-axis, so it goes rotation right-handed. This would be a vector going around that way that looks left-handed from this side. Okay. The B-type motion is the one that we love because of the two couple pendulums that are symmetric, bilaterally symmetric, make a nice motion. And now the eigenvectors for this thing, which are located here and here, and right now we've got the crank vector sitting on that negative direction. They correspond to 45 degrees and minus 45 degrees respectively. So This one right here, I guess, would be plus 45. That one's minus 45. Those are the two eigenmotions. Both plane polarizations, but they're as far away from getting far away as you can get from X polarization. So now you're going to fill up a square or rectangle that's turned by 45 degrees after you've run this thing for a while. Assuming that you have not a periodic solution, that is, that you have eigenvalues that are not commensurate, you would make this fully blacked out with ink if it was, as we say, ergodic. That is, it covers every point that is allowed by the conservation's laws. Right circular occurs at when this thing has gone 90 degrees. That's quarter wave plate. Okay, so there's a solution to that. And the ones I want to get to, of course, are more complicated. The C-type motion, just only C, only the C matrix, okay, that has the Y axis here. The pictures in a textbook put the C here, put the Y axis down. Most of the time you like to make Y axis the axis of quantization. Why is that? Well, first of all, the idea is that you're going to use the Z crank and the Y crank to produce your states. Okay, that's the idea. And the reason the Y is so cool is that e to the I times this thing, it has i's in it, is a real matrix. In other words, the actual rotation matrix, which we worked out before, was just a plain old cosine, minus sine, sine, cosine, rotation, two-dimensional, right? And totally real, right? Not true of the Z rotation, but it was diagonal. It was e to the I angle, and then e to the minus I angle of rotation, right? So the idea is to use just those two. One of them is complex, which has complex arithmetic, which can get hair pulling. But if it's diagonal, great. You only got one of them to do, and you do the conjugate immediately. Okay? And then the other one, the Y, why wouldn't you use X? Well, if you use X, which is 1, 1, it's complex. So you've got all this complex arithmetic, especially when you're talking about higher angular momentum manifolds. J equal, 1, 2, 3, 4, 5. On the wall over there is J equal 88. Okay, that's kind of the momentum we were working with. We definitely couldn't afford to do complex arithmetic with big matrices, so we picked the Y. So we do everything with Y and Z when you talk about computational simplicity. Okay, well this one just makes the rotation of the plane polarization, which I always call Faraday rotation, since that's the commonest thing until recently. All right, now there's a typical example of that, an ellipse evolving by rotating and making beats as well. This one is just a typical example. What I want to talk about are ones where you have the A, B, and C together, particularly A and B, but also A, B, C a little bit. Okay. So there's the general case. Here's the A, B type motion. Now I have the diagonal not equal anymore. You see, so this is not bilaterally symmetric. Okay, so I'm talking about a crank vector located at A minus D and 2B as its coordinates. Coordinates in the A direction, okay, right here, okay, it's just A minus D in the A direction, and that one's pretty close to it. Now I've got a little bit of 2B, so I've got just a bit of that there as well, okay. So it's some oscillator that is Still no C. So this isn't going to be anything but a standing wave, basically, if it's a quantum mechanical object. But it's going to take you on a trip into C land and then back again. And there are the components of the crank vector right there, just from the algebra that we've done right here. Okay? And there's a typical example of that. Not very much of the B, and only a little bit of A minus D right here, 3.4 minus 2.1, okay? That gives you this particular beast. You can see it has a fast axis there and a slow axis there. So that's a mixture. Now, how do you handle this, or how do you think about this? We looked at just a little bit at this, but I wanted to check you with something here. If you have an H that's real but asymmetric diagonal, that's what we're talking about now, and this is a good way to do the quantum analysis of the two states of the molecule that started the whole laser revolution. Actually, it was a maser, microwave amplification by stimulated emission of radiation. That's what maser stands for, huge long acronym. But the idea was the two states of ammonia are not classical. You can't show the ammonia molecule with a tinker toy unless you show both of them and then make a fuzzy picture of them in between those two. So what we're talking about, eigenstates of ammonia are this plus this over the square root of 2, and that would be, I'm just sketching the blurred nitrogen locations stretched out between these two places where they would have been if they were stable, and then a minus, up minus down here, and that one is definitely had to have a 0 here, so I draw it being necked off as a node right there. You see, this one is very happy to be in this region, so it will not be ever found right exactly in between there. So it's these two states that play all the roles to make a laser, to get the population inversion by being cranked an oscillating electric field from here up to here. And then you send them through something that has a non-uniform electric field that separates the ones that are excited because they're contra. You see, they want it, an electric field is applied, it pulls it this way. If it's in this state, it pulls it this way. And that's, then you just put it into a microwave cavity that has the frequency so that you can coherently excite the oscillation mode of the cavity. That's the first maser. Super Nobel Prize in an entire, can you just think of all the things that have to do with coherent radiation? All came from this. This is Charlie Towns and company. Okay. Now one of the things that we're thinking about is what does a Hamiltonian like this look like? Well, in its own basis, in the asymmetric diagonal basis, it looks like that. And I'm going to transform this thing using these two eigenvectors to see what it looks like in the B basis. Okay? And the B basis is its eigenvector basis. This plus this, that's this right here. And then this minus this, that's this one. That's this guy right here. So here are the two archetype states, okay, eigenstates, for the thing without the electric field on. Then when you turn the electric field on, of course, it gets to be some mixture of these two. Well, let's see. If I actually use the eigenvector to diagonalize this thing, what do I get? Okay? In other words, I just go through and multiply by this matrix and its inverse. It happens to be its own inverse. Okay? So when I do that, I see that I get here an A plus B, B minus A. Basically it boils down to this thing, which is that thing. And look what it's done. Where there was A, there's now B. Remember, B is a tunneling parameter. A is just the energy that it has to start with, okay? Before you do any perturbation by the tunneling, okay? And then the A goes off and sits on the diagonal now. I think it was on diagonal before, it's now off diagonal. So you just interchange A and B by doing this transformation to the eigenbasis. Kind of neat, right? But if you're going to do perturbations of eigenstates, this is the one you want to use. Now, while I'm on the subject, we were getting exact solutions for a two-state system, okay, and that's a parabola, hyperbola, up and down, okay, just like we showed. These are the actual eigenvalues. But what if I wanted to do a perturbation expansion for this, okay? And this is part of something that's in the quantum book at the end of the first unit, which is a sort of a review. What it really shows is the futility of doing higher order perturbation theory. When you're trying to get a hyperbola, right, you've got to go a long, long way before you ever get even up to here. These are second, fourth, sixth, and 10th, 8th, and 10th order perturbations of this problem. It's very unlike what we saw with the sine and the cosine, where eventually you could get a very accurate thing. You just had to take a lot of terms, right? Here you take a lot of terms and you really don't get past about there. Yeah, you know, this thing just doesn't stick well. So that's something that I think should be pointed out. That's the perturbation expansion right there. It's totally useless. So you know, keep that in mind. Second order maybe. Mostly it's first order and then second order. Takes you out a little bit, but then getting the rest of the way, not pleasant. So I thought that would be interesting to see. And also the source of the hyperbolas. If you have here the A parameter, which is the electric field dipole product, okay, and here's the tunneling parameter for the thing without the electric field, plotted in this direction, that's two cones coming together, okay. Pick a certain value of the tunneling parameter, say that value right there, and that value right there, they're your eigensolutions. Eigenenergies, actually, crossed hyperbolas, okay? And again, if this is relativity, that's your light cone, positive frequency, negative frequency. But this is a much simpler problem than that, okay? So that, you know, that's worth looking at. Ground state and excited states are sitting right there on that. Now, elliptical polarization, typical. I've already made the point that this angle right here, which is an alpha over 2, an Euler angle. An Euler angle is what describes things in the Stokes space, the spin, quasi-spin space, S for Stokes or spin. Angles from here is a, if you're using the C as your thing to nail your polar coordinates, then this could be an azimuth. This would be a copolar, right? The real polar angle is to the, you know, the c-axis. But if you're using this one, which is what we're doing, then indeed this is the polar angle of this vector measured, you know, off of this axis, actually right here. I mean, you just rotate this thing back here, and that's the beta, okay? And that beta determines how open, how far up or down in the direction of the c-axis you are. And I've got some healthy angular momentum going here, you see. And this is more like a moving wave when I put wave functions on it. It's actually got a motion. It's got a current. That's the other thing without C. see, it is a current. It's not a standing wave. It's a mode that has a current. Like a ring laser, okay, where you use mirrors that make the thing go around so they don't cross each other all the time, make standing waves. So all of that, I think, is worth knowing. Now, looking at it in 4 dimensions, it isn't really 4 dimensions. I can only pick one of the other quantities. We've got x and y here, so I pick py as the other variable. And if you do that, you start to see what classical mechanics calls the invariant torus. It's just an oscillation here, hasn't crossed the a-axis yet. So you've got pretty nice open orbits here. Now you're starting to cross as you come right to that point. It closes the donut, so to speak, for our particular view. And then go down to here and you make the torus overlap itself considerably. These are 3D pictures. These are pictures if you go back and just do the thing where you make this eye look at this and this eye look at that. You will see a nice 3D picture of both the Stokes space and the full, almost 4-dimensional description. And you'll find that this thing is a straight line relative to the coordinates that are made by drawing ellipses that go with this particular spin vector at different intervals. So you make a coordinate system on the torus and actually watch a straight line of certain slope, and the slope is determined by initial conditions here and everywhere here. All of these things have different varieties. This one is one that really shows the full 4 dimensions. There's a torus, and the 4-dimensional torus has 2 holes. One thing like this, and then another thing sort of through it like that. So one side of this thing you actually go in, and it would be a hole if I let the parameters go like that. But then there's another one where, and I think it's right here, you have a hole pointing the other way. So they're perpendicular axis of the thing that lets you actually see the 4-dimensional sphere, which is a torus. And that's, kind of neat. This is some truth of classical phase space. And there's one actually being made there. Has a hole this way, also has a hole this way. So it's really quite strange. All right. I think we probably ought to quit here. I'm just telling you some other things that are here. This is a familiar way to describe polarization by rho 1s plus and minus. These are phase vectors, rho 1 and rho 2. So the idea is to convert amplitude rho 1 and rho 2 and omega into one of our systems. So this is a common thing. And this is just a picture of where that would be used. These are equations here that are just drawing the things that we looked at before. Remember this business right here, right? Where you make an ellipse by having the position and velocity phasors. And then there's the other family of those. Where these things touch the boundaries, okay, that's where the theta angle comes in. And I just mentioned that so that when it comes time for you to make something to do with the theta, the beta angle, you can see that. So here's a conversion between those, and it's pretty easy to do that one. There's the typical Euler angles, and where this touches here, that's the phase angle. That corresponds to the phi of the Darboux way of looking at things. So this is all available. If you get deeply into polarization, this could be a help, both for here. Here's another thing you can do. If you want to go from, if you've worked everything out in the A basis, and you want to go see what the B basis is, you just do a permutation, you see. I let my balance be defined by polar angles that work on the B axis. We started with the A axis, right? You can use the B axis, that's just a turn by 45 degrees. Or you can go for the C axis, and that's a full complex thing. So just this set of equations lets you make a conversion between looking at something using the C axis, which is for most atomic molecular physics. I explained why that one is the good one to use. All of the arithmetic comes out pretty nicely, and as I said, the rotation operators are either diagonal complex or off-diagonal real. And the phase lag then shows up where these things make contact in various situations. So that's a C view of one thing. Then you can do a very quick conversion to the A view. So that's worth knowing. That's something that will maybe be of use sometimes later. I'm going to speed up here just to get you a feeling for what you do in quantum mechanics with density operators. With density operators, you're interested in making use of components that we already have. This is what the state looks like, and there's what some matrix elements look like. That's ordinary quantum mechanics. But you start playing with outer products like this. There's rho for density. It's just the psi 1, psi 2 that we've got right here, outer product crossed with the complex conjugate, the ket bra a mixture, okay, of a pure state. This is still a pure state. Then I start messing around with mostly the diagonal elements to add classical probabilities, and then I mess around with this one to make it be depolarized. Okay. So anyway, in terms of these quantities, that's what it looks like. Okay. So then you take that and expand that in terms of our old friends, B, C, and A, or Pauli X, Y, and Z. Okay, expand this, the density matrix, in terms of that. You already see it's got the form that we have. There's the diagonal form, there's the thing that has plus minus, and then there are the x minus iy and x plus iy right there. So that's what a density operator really looks like for a two-state system. Two components. Four components really, but three that count. Then you expand that in terms of this, you see. So you can write that thing just exactly the way we did everything before. Now, what do you do with a density matrix? It's got an S dot sigma, or else, if you like to use the omegas, it's got an omega over 2 dot sigma. How do you work that with a Hamiltonian and a rho? What happens there? And this is the last thing. I just want you to see it, go through it very quickly. There's the Schrodinger equation. There's the daggered Schrodinger equation you're going to need in order to talk about ket bra. So you put those two guys together. There's the density matrix. Here's the partial derivative of the density matrix. A dot on this one, and then a dot on that one. An H on this one, and an H on that one. Well, that's called the Bloch equation. Seen that? Right. That's your equation of motion. And you're going to pay for this thing if you go to higher dimensional systems, you see. Because instead of just storing n things, you've got to store n squared. These are all matrices, right? So things are going up as n squared now, as opposed to going up for n, we do ordinary quantum mechanics, right? But there's some tricks at play. This looks like a big mess when I actually work out what h rho is and what minus h rho h is, okay? I do get some cancellation. So I get a thing that looks like that. Ooh, I could do something with that, okay? Turns out, just by playing with Levitch-Vita axis, you can go ahead and write this thing. This is rho dot now, okay, IH rho dot, okay, this way. So it turns out it's the spin vector cross the crank vector. Is that surprising? No, it isn't. That's what we knew all along. That's what the Bach equation is, you see. It's just cranking with the crank, right? And that's your S dot. That's a classical equation. And that's the whole idea of density matrix, is make things classical as possible. And have the quantum mechanics to play with anyway. Okay, I think that would be better what we stop at. We're using up a little bit more time. But, you know, these are things that you can use for many years. This is going to be a way you do things for quite a while now. And we try to improve that a little bit if we can.